Hello everyone. Let us continue our lecture series on strength of materials. This is our lecture 3. In the previous lecture 2, we have discussed the strain energy due to suddenly applied loading as well as the strain energy due to impact loading. In this lecture, we are going to see the strain energy due to shear as well as the strain energy due to bending. First, we'll see the strain energy due to shear loading. For this, let us consider a block, square block, which is ABCD, and tau is the stress, shear stress, which is produced in the particular material due to the external force which is applied within the elastic limit. And the energy stored due to this shear loading is denoted by generally the energy stored due to loading is, we have already seen, as sigma square by 2 E into V. Here, since it is shear load, we are taking tau square, which is the shear stress, tau square by 2 G. G is the modulus of rigidity and V is the volume. Okay, so this is the strain energy due to shear loading. Let us look into this diagram. So let us consider a block, a square block ABCD of length L. The faces AD and BC are subjected to shear stress, and this face AD is fixed, and phi is the shear strain, what these faces have undergone. The deformed position of this block is A, B1, C1 and D. So this is the deformed position after applying the shear loading. From the previous diagram, what we have seen in the previous diagram, this is the block. Kindly adjust, it is not exactly a square. And this we have taken as A, this we have taken as B, this as C and this as D, and the deformed position, this is B1, this is C1, and the strain what they have undergone due to this loading is phi. Okay, here also the same thing, phi. From this diagram, I have already told you this phi represents the shear strain. So what will be, this is the length of the block, which is L. Okay, so what is tan phi? It is opposite by adjacent, which is B1 by L. When phi is very small, we can take tan phi as simply phi. So phi will be B1 by L. This represents the shear strain. Have a note on it. And phi represents the shear strain, which is B1 by L. Next, the force on the face BC. So force is stress into area. Here it is shear stress, and the area we have taken as BC into L. Okay. And here, if the load is applied gradually, how will be the load deformation diagram? It will be like this. It increases from 0 to P. Okay. If the load is applied gradually, it increases from 0 to P. So what will be the average load? It will be 0 plus P by 2, which is P by 2. And next, the strain energy due to shear loading. What is the strain energy? Which is load into deformation. And the load here is P by 2 and the deformation is B1 because it deforms from B, it deforms to B1. The deformation is B1. Okay, now instead of P, you are going to substitute this one. So half into P is tau into BC into L and B1. We have already seen in the previous slide the shear strain is B1 by L. So what will be B1? It is phi into L. And the next, what is this G called as? Modulus of rigidity, which is shear stress by shear strain. And from here, strain will be shear stress by modulus of rigidity. So substituting all these in the equation which we have seen in the previous slide. So we substitute all those values, and now what is this BC into L? This is the area, and here it will be tau, and here also you have tau. So tau square by 2G A into L. Area into length is volume. This is the strain energy for shear loading. We have already seen what is called resilience. So it is the energy stored, elastic energy stored due to gradually applied loading or something. So that is called as resilience due to load. What is called shear resilience? The energy which is stored due to shear loading is called as shear resilience. Let us move on to the next one, which is strain energy due to bending or strain energy due to flexure. Okay, so here we are going to consider a beam, but not the entire beam. We are going to consider a strip of beam. The strip which is of area dA and which is at a distance of y from this neutral axis. Over the small length dx, we are taking the moment to be constant. What is this? This is simple bending theory, which is m by I equal to sigma by y. So from here take stress. So stress will be m by I into y. Take this as equation number 1. Okay, generally due to normal stress, what is the strain energy stored? It is U is equal to strain energy stored due to normal stresses. U is equal to sigma square by 2E into V. Here, since we are considering only a strip, we are taking as du is equal to sigma square by 2E into dV, which is the volume of the strip. What is volume? It is area into distance. So we have already taken the area of the strip to be dA, and which is at a distance of dx, the moment is assumed to be constant, and dV is dA into dx. Here, instead of sigma, we have derived this from the simple bending equation, that is sigma is m by I into y. Okay, so 1 by substituting here, instead of sigma, m by I into y the whole square, and instead of dV we are substituting dA into dx, and when you square it will be like this. What we have seen in the previous slide is for the strip. So when we are going to take for the entire cross section, it is just an integral of that. When we integrate the energy in the strip, we'll get the energy stored in the entire cross section. So it will be m square by 2 ei square integral y square dA into dx. What is this integral y square into dA known as? It is a moment of inertia. Instead of this integral y square dA, substitute I. Already here you have I square, so it will get cancelled. One I will get cancelled, and du will be m square by 2 ei into dx. The total strain energy will be integral of m square by 2 ei into dx. Okay, this is the strain energy stored due to bending or flexure, which is integral of m square by 2 ei into dx. Thank you.